I need to advertise. All right. Well, so today we're going to get into some stuff where you can do problems and calculations. We're going to start out with units and unit conversion. So the basic idea of this is any scientific measurement has units. And all units that we use in this class can be made up of a combination of 3 simple unit types. When you get into physics 2, there'll be other ones. Charge is one. When you get into atomic stuff, there's some other one. But in this class, all units can be expressed as a combination of 3 simple types. Those are length, and the SI units for length, the Standard International or System International or something, is meters. Time, and the SI units for time are seconds. And mass. And the SI units for mass are kilograms. You'd think maybe grams because you don't have the prefix on it, but it's kilograms. And so the way that works is like, well, what about, so how do you measure speed, say, for, as an example? Well, that's a combination of meters and seconds, length and time. That you can write that as miles per hour, meters per second, that kind of thing. And every unit that we're going to use in this class can be expressed as some combination of these 3 simple types. How many people have had a class where you've done unit conversions? Probably chemistry, almost everybody, and maybe everybody, and some people's arms are tired. All right, well, so unit conversion, the idea is just like this. Like a lot of these you're used to doing just in your head, even without like a formal approach. So for example, how many inches are there in 3.5 feet? And to do that, we're going to use the fact that 1 foot is equal to 12 inches. And by the way, these are non-SI units of length. Okay. Well, intuitively in your head, you know that the answer is you just multiply that 3.5 by 12, and that gives you the number of inches. But the way that works is, think of this ratio um, 1 foot over 12 inches, and 12 inches over 1 foot as, a ratio of equivalent quantities. and therefore they're equal to 1. And what that means is that you can multiply anything by either one of these ratios without changing the thing that you started with. It'll look different, but it'll still be the same thing, okay? Because you're dividing it and multiplying it by the same quantity. So we're going to take that 3.5 feet, that's our starting value, and we're going to multiply it by one of these ratios, okay? And that's going to change the units without changing the actual thing that it represents, okay? So 3.5 feet. We're going to multiply that by either 1 foot over 12 inches or 12 inches over 1 foot. We want the feet to cancel out because we're trying to get an answer in inches. And so we're going to multiply this by 12 inches over 1 foot. Okay. And we get the thing to happen that we want. The units we're trying to get rid of go away. And so you end up doing what we knew intuitively you have to do. Take that 3.5 feet and just multiply it by 12, and that gives you the number of inches. So what is that, 42? If we had multiplied 3.5 feet by the fraction 1 foot over 12 inches, we'd get crazy units because the feet wouldn't cancel. We'd get units of feet squared over inches. We'd still have an answer that was equivalent to our first answer. It just wouldn't be in the units we want. Like you could use units of feet squared over inches as your length units, but just no one does that. We don't want to do that. Okay. Okay, so what about units like meters per second, where you have combinations of these units? So let's say that we want to go from let's say we want to convert 9.81 meters per second squared. This will come up again later, but this is the SI units for acceleration. And 9.81 meters per second squared is the acceleration of an object in free fall at near the surface of the Earth. So we want to convert this to units of feet per minute squared. Using the fact that 1 foot, no, meters, 1 meter is equal to 3.281 feet, and 1 minute is 60 seconds. So we have 9.81 meters per second squared. And I'm going to write this as seconds times seconds. Okay, so we're going to start with that. And we're going to multiply it by either 1 meter over 3.281 feet or the reciprocal of that to cancel the meters so that our length is in feet now. So, well, the meters are in the numerator, so we want the meters of our conversion factor to be in the denominator. So I'm going to multiply this by 3.281 feet over 1 meter. Okay. And if we just keep up with what we're canceling, now we don't have units of length in meters, we have it in feet. That's what we want. But our units of time are in seconds. Okay. So now we need to cancel these seconds. And we have it twice, so we have to do it twice. Our seconds are both in the denominator. So we want to have our conversion factor seconds in the numerator. So we'll multiply by 60 seconds over 1 minute. And that cancels one of these seconds. You're just doing this math as if those are algebraic variables, as if they're x or y or whatever. But we still have this other second left, so we have to do it one more time. So multiply by 60 seconds over 1 minute. And that cancels the other seconds. And so now our units are right. We have units of length in feet, units of time in minutes. Multiply that all out. You know, all you're doing now is just multiplying out all those numbers. And you get an answer of 115,872 feet per minute squared. Yep. No, I'm not. In this class, just keep some decimals, whatever feels right to you. I don't have to worry about that because the chemistry people are going to worry about it so much. I'm going to save the time. And the way I happen to write this, you don't have to do this. And if you have a way of converting units that you think about it differently than this, as long as it works, that's fine. This is just a way that works. But I tend to write this as 9.81 meters. And there's the fraction bar. And then on the bottom, I have seconds times seconds. And then instead of parentheses, just to save pen strokes, I just have vertical lines. So then it'll be 3.281 feet, 1 meter on the bottom line, 60 seconds over 1 minute line, 60 seconds over 1 minute. The cancellations all work out the same. It's just, I don't know, to me it's a little easier to visualize, but it comes out the same. Okay. Any questions about that? And then we're going to use unit prefixes pretty often. So the ones that we're going to use the most are nano, which you can think of as meaning times 10 to the minus 9th. Micro, you can think of as meaning times 10 to the minus 6. Milli means times 10 to the minus 3rd. Centi means times 10 to the minus 2. Kilo means times 10 to the positive 3rd. Mega means times 10 to the 6th. And giga means times 10 to the 9th. Okay, so that's from smallest to biggest. If you have 5 nanometers, that's a tiny distance. If you have 10 gigameters, that's a huge distance. Or 5, whatever the number was I used. Any questions about the meaning of those prefixes? So if you have to go back and forth between things with prefixes, let's say express 50 microseconds. I guess so I didn't give these abbreviations, but nano is represented with a lowercase n. Micro is represented with a Greek letter mu. Milli is a lowercase m. Centi is a lowercase c. Kilo is a lowercase k. Mega is an uppercase m. And giga is a uppercase G. Okay, so say we want to express 50 microseconds, or let's say negative, well, no, let's keep it like this. Express 50 microseconds in units of gigaseconds. I don't think I've ever seen that unit, but it's a thing. Okay, so how would you do this? Well, there's 2 steps. First, we want to get rid of the prefix micro, the mu, and then we want to add the unit giga. So the first step is, so how do we get rid of, how do we express 50 microseconds just in seconds? Well, since micro means times 10 to the minus 6, you can just replace the micro with, so 50 microseconds. This micro just means times 10 to the minus 6. So this is equal to 50 times 10 to the minus 6 seconds. So getting rid of the prefix is easy. And now we have to add a new prefix. So the second step is we're going to use the fact that 1 gigasecond is equal to 1 times 10 to the 9th seconds, right? Because that's what giga means. Any questions? Okay, so we're going to start with our current value of 50 times 10 to the minus 6 seconds. And now we're going to do a unit conversion where 1 times 10 to the 9th seconds is equal to 1 gigasecond. The units of seconds cancel. And now you're just using the exponent rule. So 50 times 10 to the minus 6 divided by 10 to the 9th is 50 times 10 to an exponent of minus 6 minus 9. So that's 50 to the negative 15th gigaseconds. And that answer is correct. I skipped some stuff. That answer is not correct, but this answer is correct. 50 times 10 to the minus 15 gigaseconds. And then this is kind of an ugly hybrid between a standard number and a scientific notation number. For scientific notation, we just want one leading value before the decimal point. So this is equal to 5.0. If you're going to make the first half magnitude smaller, you have to make the second half magnitude bigger. So this is 5.0 times 10 to the minus 14 gigaseconds. Any questions about that? Okay. So now we can get into the first sort of physics topic. And that is particle kinematics along a line. Okay, well, there's 3 bits of information in this long title. One, it deals with particles. Second, it's kinematics. And third, it's along a line. So what do these things mean? So particle means that we're treating objects as if they have no length dimensions. You know, it's like the size of a point, infinitesimally small. They do have mass, though. That won't come up for a little while, but and the object's location is the object's center of mass. When you think of particle physics, what that generally means is that you're dealing with things that are smaller than an atom, parts of an atom. Okay, that's not what I'm talking about here. It turns out that, you know, like a lot of the important physics right now is going on with subatomic particles. And things that are really small, it's pretty reasonable to treat them as if they have no length dimension. So that's why that's called particle physics. But you can treat anything like a particle if you just throw away the information about its length dimensions. Like, for example, if you're doing calculations involving planetary motion, people treat those as particles almost always. Really, the only thing that you need to treat something as a particle is you need to not be interested in the orientation of the object. Okay, so if you want to track Jupiter's path as it goes around the sun, and you don't care what direction the spot on it is pointed, then you treat Jupiter as a particle because it's a little simpler to do. Okay, but you can't can't calculate an object's orientation this way. So you can track where it goes, but you can't track which way it's facing. There are a lot of times when you need to know an object's orientation where that's important information, and in those cases, you can't do this. But we're going to start out by just tracking the location of the center of mass of objects as the object moves around. And if it rotates or whatever, we're just uninterested in that information. Okay. The second bit of information in this title is kinematics. Kinematics, that word is used as opposed to kinetics, which is the next thing we'll study, and it seems ridiculous, unnecessarily confusing that these two topics we're going to deal with have almost identical names, but I don't know. People already named them. We don't get to really rename them. So kinematics is the one we're starting with. It's the simpler of the two. And kinematics deals with describing an object's motion without the causes of the motion. And the causes of the motion we'll think of as force and mass. Another way you can think of this is it's just relationships between time, position, velocity, and acceleration. So that's all we'll be doing in this first topic, is dealing with those four things and a couple of closely related things. And then along the line is pretty self-explanatory. So eventually we'll be dealing with things in 2 dimensions. Most of the class will be dealing with things moving in 2 dimensions in a plane, like moving along the board. But we're going to start out by just thinking of things that can either go forward or backwards along a line. So let's think of this as at any instant, there's only 2 choices about which way to go. So like if this is the line and this is the particle moving along the line, it can go this way or it can go this way. We're going to see that that's really easy to deal with mathematically, because if there's only 2 choices of where to go, you can call one of those positive and one of them negative, and then the sign of the numbers that you're dealing with represents which direction it's going. Okay. Later on, when we go into a plane, you have an object here. It can go infinitely many directions, right? And we obviously don't have infinitely many signs. So positive and negative aren't going to be enough to tell us direction. And so we're going to have to come up with a new thing, which is vectors. Okay. But we're going to start out with these concepts just in the simplest mathematical way we can, just representing the direction by the sign. Yep. A curvy line, this applies in some ways to curvy lines too. If you throw out the stuff that's going on, if you throw out the stuff that's going on perpendicular to the curve that it's traveling along, this gives information about the stuff that's parallel to it. We haven't talked about enough really to make sense out of that, but you can think of it as like, yes, this stuff works, but you have to be careful. You know, you can use it, but you have to be careful. Any other questions right now? All right, well, obviously, since we're dealing with relationships between time, position, velocity, and acceleration, we have to define these things. So I'm going to start out by defining position. Okay, so say that you have an object at a given location. Okay, so like, have you seen my chicken? Yeah, it's over by the store. You know, that's a location, a physical place in the physical world. What does it take to describe that location numerically? You know, what does it take to assign a position number, a position value to this object's location? A numeric value to the location. Well, it takes two things. First, you have to choose some reference location. That's our zero position. That's like where we're going to start measuring from. And then second, since we're dealing with motion only along a line, and there's only two possible ways you can go, we need to choose a direction that we're going to call positive. So we have to choose a positive direction. Okay, so let's see. Starting to realize why I didn't have this as a bicycle in my notes. Okay, getting there. So this bicycle is moving along this line. Okay, and the center of mass is, say here, the center of mass actually doesn't have to fall on the physical body. That's sort of an odd factoid. You know, good high jumpers, you know, high jump, they use the back flop thing. Can you picture like they run up, turn around, and go over backwards? The reason they do that is because that way of doing it is very efficient at getting points of your body higher than your center of mass at any instant. And so a very good high jumper can actually get their entire body over a bar, and never at a single instant is their center of mass above the bar. Their center of mass goes straight under the bar, and one by one, each point gets over the bar. That's pretty cool. Because your center of mass height is just determined by how well you can jump. But if you can get your body higher than that, then you can get over a higher bar, you know. Okay, so what's the location of this? You know, this is the line of travel. So we can see physically the location of this bike rider, but what's it going to take for us to put a number on that? Okay. So the way this works is, first, somewhere along this line, we're going to choose our 0 position. Okay, so that's arbitrary, although once you choose it, you have to use it consistently for the whole rest of your calculation. Okay. And then we have to choose a positive direction. There's only 2 choices of direction. It's along that line of travel. And we could choose either one. Let's say that we choose the positive direction to be this way. Well, now that we've chosen that, we can just measure the distance from the 0 position, that reference, to where the person is. Let's say that that's, what does that look like? 2.5 meters. So then numerically, what's the position? The position is a distance of 2.5 meters. And then when you start in the 0, are we going in the positive direction or the negative direction to get to the bike? Negative, so the answer is negative 2.5 meters. That's the position. Any questions about that? Position units are always length, and so if you're in SI units, position is in meters. Okay, so I want you to notice a couple things about this. So once you choose a positive direction, the sign of a number is equivalent to an arrow in space. So it's either that way along the line or that way along the line. And so you can always represent the direction in 2 ways. You can represent it by pointing an arrow in the direction of the value, or you can do it with the sign of the number. Okay. I mean, we're always going to do it with the sign of the number, but I want you to get used to this idea that the sign of that number represents an arrow. They're equivalent to each other. So like you could think of this as the position is negative 2.5 meters, or you could think of it as the position is 2.5 meters that way. Okay. If you also choose an instant that corresponds to time equals 0, then you can plot a position versus time graph. And plotting a position versus time graph is equivalent to representing the position as a function of time. Yes?
Was that also part of the notice?
No. You should still notice it, but it's not part of that notice statement. So think of choosing a time equals 0 as like when you click your stopwatch on if you're trying to time something. Like when you time a 100-yard dash or something, there's a specific instant that you start your stopwatch running, and that's when they start running. You know, if someone was like, time me for the 100-yard dash, and they run, and you're like, what? And you're like, 6.5 hours. And they're like, what? And you're like, yeah, I started it sometime earlier this morning. They wouldn't be very happy, you know. Like when you choose your time equals 0 instant, it, you know, affects the answer you get for what time an event happens. Okay, so let me do one. How much time do we have? Yes, let me do this. It'll be quick. So let's say that there's a swimmer standing on the shore wearing swim trunks. And there's a raft out here. And he wants to swim out to the raft. And let's say the distance between them is 50 meters. And let's say it takes, how long does it take to swim 50 meters of 2 minutes? Let's say it takes 120 seconds to swim to the raft. Let's say that we want to plot a position versus time graph where the position equals 0 is on the shore, and the positive direction, well, let's choose sort of an unusual one for this. I mean, you can choose anything you want as long as you're consistent. Let's choose the positive direction away from the raft, so opposite the direction to the raft. Okay, so either way, the motion, so if this is the line that the swimmer's moving along, and he starts out here at the shore, and he ends up here at the raft. Oh, and I didn't give, let's say also, the 0 time is when he starts swimming. If a problem doesn't say anything about that, you can just always assume that 0 time is when the motion starts. Okay, well, the swimmer is at the shore at 0 seconds. And what's the position of the swimmer at the shore? 0. And we chose this as our 0 position, and we chose this as our positive direction. When the swimmer gets to the raft, the time is 120 seconds. And what's the position? Yep, the distance is 50, and then it's in the negative direction, so this is negative 50 meters. And so a position versus time graph, we start at 0, 0. We end at, not there, but we end at, damn it. So that's 120 seconds. We end at a position of negative 50. And so the graph looks something like that. Okay, and what that graph looks like is dependent on your choices of those 3 things. The time equals 0, the position equals 0, and the positive direction. Okay. I said, so we're always going to, this is the last quick thing. We're always going to draw our graphs with position on the vertical axis and time on the horizontal axis. We're always going to represent position as a function of time, not the other way around, not time as a function of position. You could think of that as just sort of a convention. That's what people do. But can you think of any reason why we would do it this way and not the other way? Yeah, that's totally the right idea. The position you could end up, he could swim back and end up back at position 0. He could end up at a certain position 1,000,000 times, but a time only happens once. And so that's the definition of a function. You have to have just a single value for the function once you choose a value of that independent variable. So it doesn't work the other way. It wouldn't be a function. So without a function, you can't take derivatives. There's a lot of stuff you can't do. Okay, see you tomorrow. Look, later on today, I'll put some problems up that you can work on.